This is the James Webb Telescope project by Ashwin Tennant, Scott Yap, and Ivan Gabestro from Abingdon School.
And this is a list of the things that we are going to talk about in this presentation.
We have been working on data provided by the Cosmic Mining Project from the Institute for Research in Schools. We have been classifying celestial objects into types based on their spectra. Before this, we had already completed 2 training sets for practice. We entered data into a table with the headers shown in the bottom right of this slide. We were also provided with a visual image of the celestial body, which helped identify noise.
So for our method and approach, we would do this in a few stages. First, by just looking at the image of the star, before then looking at the general shape of the graph and its more specific features. We completed this work efficiently by splitting up the task once we all had a good idea of what we should be doing. Then we'd always make sure we agreed on the final classification as a group at the end.
Before identifying the celestial objects, we had to understand the key terms in the header of the table. So the redshift is the shift to the right in the continuum of the spectrum. The continuum is the gradient of the line in the spectrum. A stellar component is the peak in the optical part of the spectrum. The red axis is the presence of continuum at longer wavelengths. And the absorption is a dip in the spectrum, emission is the bump in the spectrum, and the atomic emission lines are prominent narrow lines in the spectrum.
We encountered some difficulties. For example, limited information due to an early cutoff at 15 microns, or many atomic emissions. To overcome these problems, we used a high-resolution spectrum shown in the top right of this slide, which gave us a larger range of wavelengths. We judged the difficulty with a confidence rating. Sometimes we instead compared our spectrum with a model answer to help us identify the celestial object.
This is an example of an easy classification. Looking at the continuum, it rises at first before turning over above 25 microns, which strongly suggests it's a planetary nebula. Although it appears to have some absorption regions, perhaps indicating a forming star, this is outweighed by the clear trend line, indicating that the initial guess of a planetary nebula was correct.
This is another example of a trickier classification. So as we can see in the spectrum, it is cut off at 15 microns. So this shows that we have to make sure we look at the x-axis. Also, the continuum above doesn't reflect the object that we are looking for. So we thought that it is a planetary nebula due to its continuum, but instead it is actually a forming star. But after looking at the high resolution spectrum, we can see that it is actually a forming star. So it shows that in the future, we have to make sure we check out for different spectrums and the range of wavelengths.
2 telescopes were relevant to this project: the Spitzer telescope, which the data was taken from, and the James Webb telescope, which we identified potential targets for.
The Spitzer Space Telescope was the first to see light from outside the solar system and was active for 17 years until very recently, January. It orbits the Earth, so the light from the stars is not obscured by an atmosphere and provides spectra mainly in the infrared region of the electromagnetic spectrum. The James Webb Telescope is a space telescope which will be the Hubble Space Telescope's successor. It is the largest and most sophisticated telescope ever built, using many different instruments to gain a whole range of different pictures to analyze unknown objects in great detail.
Now we're going to talk about the different stages of the life of a star. So forming star is the creation of a star when gas particles and dust are pulled together under gravity. Forming stars mainly have low flux density at shorter wavelengths, but gradually increases in longer wavelengths. In a typical spectrum graph, the forming star has the rising continuum, no stellar component, strong red excess, and absorption at 10 micron. There are also different types of forming stars called young stellar objects, and sometimes we have to identify it from being a YSO1 or YSO2.
This is an example of an ordinary star, which means it is in its main sequence. It is currently fusing hydrogen into helium, and its weight is balanced by the force exerted by fusion. The star remains at the same size during the main sequence, which is also the longest part of the star's life. Some features of this star are a strong stellar component, a falling continuum, and a weak red excess.
An evolved star has reached the end of its main sequence. It swells into a red or supergiant, as it now has to fuse heavier elements than hydrogen, which releases more energy and pushes the core of the star outwards. We can identify evolved stars by their falling continuums, as well as absorption regions indicating the abundance of these heavier elements which the star is fusing, such as oxygen and carbon.
The Planetary Nebula is formed at the end of the life of a red giant. It has features of rising continuum, no stellar component, strong red excess, and a few emissions. And the difference between the Planetary Nebula and a forming star is that at the end of the wavelength, it goes down.
We then studied some relevant topics, like how spectroscopy works, electromagnetic radiation, Wien's law, and the Rydberg formula.
Spectroscopy is another method for analyzing the light coming from stars, and hence their chemical composition. We see the light from stars as absorption spectra, as electrons of elements within the star will absorb light of specific frequencies corresponding to the difference in energy between two energy levels. The wavelengths of these lines can then be calculated using the Rydberg formula for simple elements shown here.
The Herztsprung diagram also provides a different approach in identifying the stars through their surface temperature and luminosity. It is a plot of stellar luminosity against surface temperature. The x-axis, as you can see, is labeled as temperature, or sometimes can be labeled as spectral class. The y-axis is labeled as luminosity, or the absolute magnitude of the star. As a matter of fact, the Herztsprung diagram is related to the Stefan-Boltzmann law, which states that the luminosity is equals to the surface area of the sphere times the Stefan-Boltzmann constant times the temperature to the power 4. Hence, the luminosity is proportional to radius squared. So the greater the radius of the star, the higher the luminosity, which shows that it locates higher in the diagram.
Wien's law states that peak wavelength is equal to Wien's displacement constant over temperature. The spectrum on the left is an ordinary star, whilst the right is a planetary nebula. As we know, the nebula has a lower temperature than the ordinary star. Wien's law suggests that the nebula would then have a higher peak wavelength, which, looking at the spectrum, seems to be true. The ordinary star's spectrum also supports the law as it rises towards the shorter wavelength, which are peak presumably out of the range of the given wavelengths.
Here is a summary of our personal reflections. Overall, we felt that although the work was quite boring at first, we definitely all got something out of researching this topic in depth, and hope that this helps us in our A-level studies and beyond.
This is a rough timeline for our project. So at the start of the year, we decided to do James Webb project. After that, we evaluated the final training set data and submitted it. And then after that, we did the unseen data, and then also submitted it in the end. And then after doing all these training data and unseen data, we started on our research on related topics like spectroscopy and Wien's law. And then at the end, we finalized by doing the presentation and typing out our report.
This slide is based on criteria in the student form, and that all the criteria had been met is shown here.
And this is the end of our presentation. Thank you for listening.